Thank you, Professor Singh. I had the opportunity after joining here to work with Professor Singh for a couple of years. And at the inception, it is usually a crisis period. And I must say, Professor Singh had acted the role of my friend philosopher guide. So that's how we have been able to proceed through. I'm also thankful to Professor Esar Kumar and the organizing committee for giving me this opportunity. As I was sharing with my colleagues, after I joined here, I got a lot of invitation to speak, but mostly few words in inaugural session or an overview. Hardly I got an opportunity to think on, speak on the work where I was associated directly. So when Professor Esar Kumar asked me to present a lecture, I decided that I will go for some work where I was directly associated. This is a doctoral work of my student, Dr. Oreidis Sinha, who is now Associate Professor in Kaji Nazrul University, Asansol, West Bengal. And the subject is the correlation of the correlation of microscopic and macroscopic behavior of shape memory alloy. Purposefully, I decided to speak on this because nowadays we talk a lot about smart materials, smart system, smart technology. And most of us carry a notion that metallic materials are dumb. They cannot sense, they cannot respond, they cannot act smartly. Particularly, I thought this lecture, keeping in mind about the future of my students, I wanted them to be here. I find only a couple of them. So I just wanted to convey them. Metals are always not dumb, but they are truly smart. People identified smartness in metal long back in 1932. Professor A. Olander, he discovered shape memory behavior in metals, and it is in practice over a wide range of areas, starting from structural systems, construction, aerospace, energy, particularly healthcare. From 1963, when Wheeler in Naval Ordnance Laboratory discovered NITI alloy, they add the abbreviation of Naval Ordnance Laboratory, that is, they call it NITI-NOL, right? So that is the subject I have decided. But before going to the subject, I would like to discuss few things about Martin-Seligg transformation. I know all of us here are aware about phase transformation. It is transformation of one particular crystal structure to other with or without composition change. And this transformation requires certain activation. It can be thermal or chemical, or it can be mechanical. In some of the transformations, atoms need to diffuse over long distance. Long distance, I mean few order of magnitude or multiple of interatomic distance. It moves from one place to other, which is multiple of one interatomic distance. And it needs thermal activation. They are thermally activated. So we call it diffusional process or diffusional transformation. When atom moves to this particular distance, we call it diffusion. There are some other transformation which occurs without any significant movement of atom. If there is any, it is less than 1 intermediate atomic distance. And the atom moves in coordinated manner. Movement of each atom is guided by other, like a military troop. In a military troop, movement of individual member depends on other, and it is coordinated, unlike civilian. So diffusional transformations often people call civilian transformation, and this kind of transformation, diffusion-less transformation, people call military transformation. And the driving force for this transformation is shear, not chemical energy, not thermal energy. It is shear driven. Here is an example. This is for steel. Popularly, there are two crystal structures which we use in steel. One is austenite, which is a FCC structure, and other is ferrite, which is usually a BCC structure. So, Bain had shown, see, this one is austenite. You can see there is atoms at this surface. So, this is face-centered cubic structure. So, we have considered two austenite cells, okay, two austenite unit cells. Now, Bain had shown that it is possible to identify a body-centered cubic cell within the combination of these two face-centered cubic cells, face-centered unit cell, right? So it is possible that the face-centered cubic structure may transform to body-centered cubic structure without any significant movement of atom. It is well delineated within the FCC structure with the atomic locations which were there in FCC. But this can be necessary but not sufficient. For any transformation to take place, we need a surface. There has to be a surface. So there has to be something which will create an interface between these two entities. This is a ferrite and FCC austenite. So Bain proposed a model where he considered a homogeneous shear. And when people observe, see, we observe something in reality and we try to create a model. We often say there is nothing FCC, BCC in reality. In reality, atoms are only stacked. Atoms are organized. Our knowledge, our intelligence have developed model from the stacking sequence. Stacking occurs by virtue of, for the need of lowering of energy, right? And we, in our mind, in our intellectual ability, we create certain model. That's why we have created FCC, BCC. Material doesn't know what is FCC, what is BCC. So this is model which we have created, and this model help us to explain the behavior of material. So it's like that. So martensitic transformation was already observed, and people were trying to understand that how come something can happen without diffusion, without long distance movement of atom. So Bain proposed that there can be a shear which will compress the z-axis by 20% and x and y-axis by 12%. So the BCT, this is body-centered tetragonal. What comes out of these FCC unit cells is basically body-centered tetragonal structure, where C-axis is more than A and B. So to match them, to make it BCC, he considered a compression which transforms the BCT crystal structure to body-centered cubic structure, where A equal to B equal to C almost. And when this homogeneous shear occurs, you can guess an interface can be created between the two entities. There can be an interface because there is a shape change, right? So for martensitic transformation, two things we require. One is shape change. Whatever shear we apply, that should result in one, change in crystal structure, and second, change in shape. But the transformation proceeds within the FCC. The BCC or BCT grows within the FCC. So, there has to be some interface. What is the nature of the interface? So, Bain proposed a model to conceive this kind of homogeneous sphere. We have a sphere. Let us compress it. It will expand. So, if you consider WX line, W has been displaced over W dashed. Y has been displaced over Y dashed. Both W and W dashed are contained within the sphere and the ellipse, isn't it? This W and W dash are point within the sphere and within the ellipse. Similarly, Y, Y dashed. But they have displaced from one place to other. One of the conditions for having the continuity of the interface is to have a line which will pass through perpendicularly between the two faces and will remain undistorted and unrotated. There will be no distortion. So we can find one line if you rotate it by some angle theta. So Y coincides with Y dash, and Y, Y dash and Z, Z dash is a common line between the sphere and the ellipse. You people can see that? Right? So this we call an invariant line. We may consider this as invariant line. So whatever changes happen between FCC and BCC, the line is not affected. Right? But later on, when people observed, we had better and better microscopic facilities, and people observed the features which occur on the material after transformation. This is the parent phase, gray one, and this is the martensite. So people find that there is some deformation at the surface. After martensitic transformation, there is some relief effect. Some distortions are observed at the surface. So what is that? So there is a crystal structure change and there is a shape change. That's why certain relief is observed. But what is this kind of relief? People drawn certain scratches on the surface randomly, and they read the distortion in the line. And when they studied the distortion matrix on the scratches on the surface, they found it is invariant plane shear. That is, it is kind of shear when one face transforms into other and the interface remains invariant, undistorted, unrotated. But Bain model could predict an invariant line. So Bain model was not sufficient to describe the martensitic transformation as it was found to happen with an invariant plane strain. That is, there has to be an invariant plane. What is invariant plane? You can conceive, you draw a dotted line over here, create a plane. This plane separates martensite and austenite, and there will be no distortion, no rotation in this plane. And the strain, when you move ahead within the martensite from this plane, the strain will increase with distance. So this is the character of invariant plane. So we need to have a phenomenology which can justify the occurrence of invariant plane. There is a simple explanation. Say this is a shape and crystal structure of austenite. So if you apply a shear, if we apply a shear in this direction, we can create the shape we require for martensite. Right? Now again, this is a shape we have created, but crystal structure is not established. So for that we need another shear. So we have a martensite crystal structure, but again shape is distorted from here. So we need something to bring back this martensite to this shape. Then our explanation will be complete. And these two shear is equivalent to Bain strain, that is rotation and Bain strain. This homogeneous shear and rotation, R and B. We call rotation R and homogeneous shear as B. So whatever we come across, under this RB combination, that is invariant line, this will also give an invariant line, but we have two shears, and we have a situation where we have the martensite, but we need something to have this shape. Just imagine, if I cut this portion, if I cut this particular portion, this triangle, and I fit it over here, what is the result? We can regain the shape. That is what we do. It doesn't occur by diffusion, but we create certain slip. Certain slip occurs here, like this. Dislocation moves from one into other. If we apply a shear, we generate dislocation, and this dislocation moves from one into other. And when dislocation moves from one into other, the atomic arrangement within the crystal is not changed. That we know from basic metallurgy. The atomic arrangement remains same. So lattice remains invariant, right? But the shape can be reorganized either by dislocation or by twin. So that we call invariant lattice strain. So with the homogeneous strain for formation of martensite, we need this inhomogeneous strain. We need a macroscopic, this is microscopic homogeneous strain. And this is happening at the surface. So this is basically macroscopic. So we need a macroscopic inhomogeneous strain to convert the wrong shape to the desired shape of martensite. So for completion of martensite, we need one invariant plane strain and other invariant lattice strain. And this lattice strain occurs in terms of dislocation and twin at the surface. And this changes the behavior of martensite. Now regarding driving force, as I have mentioned, it is not chemically driven. It is not thermal driven. So this is the austenite free energy line, and it is the martensite free energy line. We know, perhaps it is taught in mechanical engineering also, when they intersect, it is the equilibrium. We call it T0, right? So below the equilibrium temperature, there is a temperature Ms where we achieve some energy, some thermal energy, which transforms austenite to martensite. So we require the martensite to be cooled down below equilibrium temperature at certain lower level below which martensitic transformation will take place. And it is, you may call it thermal driving force, or you may call it chemical driving force. But what about shear? Shear occurs at a temperature above martensitic start temperature. And if you go at a temperature above martensitic start temperature, you will find the thermal driving force is less, which is less than that minimum required for martensitic. This is minimum driving force, minimum energy required for martensitic transformation. But at any temperature above Ms, the driving force is much less than required for martensitic transformation. So that can be compensated by mechanical driving force. The shear compensates the deficiency in driving force and completes the necessity of the driving force requires, right? So application of shear may cause martensitic transformation above a temperature Ms, right? And that can be stress or strain. How does stress and strain induce the transformation? If you follow the yield stress of a material, it reduces with temperature, right? So if you apply certain stress, that may bring in certain transformation elastically. That is elastic transformation. It will be reverted. Even if there is a transformation, that will be reverted. So it is basically elastic transformation up to yield strength. But above yield strength, there will be permanent deformation and the transformation will be permanent, right? So we call it Ms sigma up to yield stress, and the permanent deformation which induces martensitic transformation, we call it Md. So it occurs between Ms and Nd temperature. Now, the martensites where invariant lattice strain is twin, that demonstrates certain unique behavior. For example, let us consider austenite and let us take a single crystal of austenite, say a grain of austenite. Let us consider an austenite grain, right? cool it down, it will transform into martensite. But for compatibility between plane and line, there are 24 possible variants of martensite. Variant means 24 possible combination of plane and line, crystallographic plane and crystallographic line. 24 combinations possible, but all do not form. Those variants which are favorably oriented in the direction of strain, those are formed, right? So these variants are formed which are randomly distributed. Now the unique feature of twin martensite is that when you apply strain on that or stress on that, these variant will reorient. This variant will try to orient in the direction of minimum strain energy or favorable strain direction. All the variants will try to orient in the favorable strain direction. And as they are in same orientation, they will try to reduce energy further by combining with each other. There will be coalescence of these variants. First, they will orient in one direction and they will coalesce, right? And when they coalesce, they become a single crystal of martensite. If all the variants reorient and they coalesce with each other, what it becomes? The product is single crystal martensite. So we have single crystal martensite. Now, once it is single crystal, when you withdraw the load, there is no change. But as it is single crystal, when you heat it up, it will go back to the original austenite grain from which it was formed. It will retain the shape, size, everything of the original austenite grain. So we can say the martensite can memorize the austenite. That's why it is called shape memory alloy. It can memorize. If you combine all the austenite grains together, the same thing. Suppose it is English L letter. Suppose this is an English letter L. Now you deform it. You quench it, form the martensite, deform it, have a single crystal, unload, and go back to austenite. Here you can deform it to I. Say L I deform to I, right? You unload it and heat that I to austenitic temperature. You will get L. So that is simply what happens. Now, there are two possibilities. Why does it happen? It is by virtue of its stress and behavior. If you look at steel, if you stress it and withdraw the load, there is a minimum about 0.5% strain which you can recover. That is the elastic strain. But in case of nickel titanium alloy, first it is elastically deformed and then the strain is accommodated within certain plateau. That is, austenite forms, they get twinned, right? By virtue of, but there is no necessity of stress. Once that is saturated, then once it reaches the CRSS, critical resolved shear stress, plastic deformation occurs and it gets saturated. That is how it behaves. Now, if you withdraw the stress from this point, you can see that this much strain can be recovered. It is about 8%. So you can recover about 8% strain, which is distinct, not available in other materials. Here we have seen this shape recovery or shape memory occurs only when you heat it. So it is one direction. So this we call a one-way shape memory. It is from martensite to austenite. But imagine you have two springs of two different dimensions, right? At martensitic temperature, you give a shape to the spring. Heat it at austenitic temperature. You give another shape. And maintain these shapes at these two temperatures and continue this cycle for n time. 10 times, 20 times, 30 times, you do this. Take it into martensite, give it a length, heat it up at austenite, compress it, give it a length. Do this for 20 times. After that, you just change the temperature. The material will attain this particular length at martensite, and this particular shape at austenite without application of any strain. So this can, by virtue of strain, this we call straining. When we are straining at a particular shape in austenite and at a particular shape in martensite, during the training, it keeps in its memory, in its structure, the shape, size, dimension of both the systems. And further, after completion of training, you leave it on its own and just change the temperature. It will move from one shape to other. This we call two-way shape memory, where the system remembers the shape of both austenite and martensite. And this is the stress temperature behavior. So as I have mentioned, as this is recoverable, so it occurs below the yield strength, right? And when the transformation occurs below austenite's start temperature, right, we call it shape memory effect, shape memory region. And when it occurs above MS temperature, even in austenite, suppose you have austenite, you apply certain strain and remove it. Apply certain strain, suppose this is austenite. I compress it. When I withdraw the strain, it gets back to its original shape. So that we call super elastic behavior. And this occurs above austenite start temperature in austenitic region. And in between there can be an overlap. So this occurs, essentially, this occurs below yield strength, because before plastic deformation starts, that's important. No permanent plastic deformation can be up to this range of strain. And it occurs in these three distinct regions up to austenite start temperature. It is shape memory region, as I have said. It occurs in martensite. In austenitic region, it occurs in austenite. We call it superelastic. So this is basically background of shape memory effect. Now we can see the whole thing is very coordinated, very systematic, right? So it calls for a very organized microstructure. If there is extreme randomness, extreme misorientation, large amount of defect, you don't get what you want. But at the same time, nickel titanium itself is not very strong. Our intention, we actually thought, this was the basis of our work, we actually thought if we can strengthen this alloy by certain hardening mechanism, two common hardening mechanisms are either cold deformation or precipitation in metallurgy. So if we can strengthen this alloy, we didn't know how microstructure affect shape memory behavior. We had no idea, simply. When we were studying this, and when we got a piece of nickel titanium alloy, we thought we will work with this. And what we can do? We thought if we strengthen this alloy by some way and increase the requirement of critical resolve shear stress, that means we can delay plastic deformation. If we can enhance the critical resolve shear stress, we can delay the onset of plastic deformation, and that is why we can increase the recoverable strain. That is what we thought. That is where we started the work. So we conducted different experiments. Sir, just tell me when 25 minutes are over. Rest I can cover by 10 minutes. That is my work, not much interesting. And this is nickel titanium alloy. What it is basically a 50-50 composition. Nickel titanium phase is an intermetallic phase having 50 nickel, 50 titanium, right? And we have two intermetallics associated with this, Ti2Ni and Ti-Ni3. So any fluctuation from composition may give rise formation of this intermetallic phase. And we find that MS temperature is very sensitively dependent on nickel content after 50%. So if there is any fluctuation in nickel content above 50%, the MS temperature changes drastically. As such, in 50-50 composition, the MS temperature is 63 degrees centigrade. Now, it has also been found that if for some reason martensitic transformation is constrained either by strain or by certain barrier, it can take alternate path. It can B2 austenite, high temperature phase, it is cubic. Low temperature phase, we call it B19, it is orthonomic phase. It can happen directly, but it can also happen, it can also take a different path where an intermediate phase from a pre-martensitic phase form, which we call R phase. And why I am mentioning this, I will come to that. And this is also verified by DSC experiment. So if you heat it, martensite transforms into cubic phase, and when you cool it down, B2 may go to R and R may go to B19 dash, that is martensite. As it happens for epsilon martensite in case of steel. Very often in steel, we get alpha dash through epsilon, gamma to epsilon to alpha dash. So it happens similarly. So we thought of some certain experiment, and first thing that occurs in our mind is aging, because we have seen there are intermetallic phases associated with the 50 titanium nickel composition. So if we do certain aging, we expected some precipitation will occur. We deformed it by aging because deformation creates a strain field which accelerates aging and results into uniform deformation of fine precipitates. So we deformed it as ice water, and we also deformed it at very low temperature. Why? Because the difference between Coin temperature and MS temperature is the driving force. It is somewhere, I'll have some equation. It is Westin and Marburger equation. The equation is simply volume fraction martensite is 1 minus exponential beta into ms minus t coh. So ms minus t, that is the temperature difference between ms and t, is the driving force. Here we have very low temperature gap between, it is only 63 or 64 to room temperature, right? So very often people come across remaining austenite in the system. So they, instead of fully martensitic, they get martensite austenite mixture. So that's why we quenched it at a very low temperature, cryogenic temperature, so that there can be very high driving force. We deformed it there and we conducted aging. And this is how we determine recoverable strain, how martensite recovery experiment is conducted. This is very simple. We have a roller, we have wound a wire around the roller. Now when we release the load, there will be a spring back. Right? It will go back to some point. And when you heat it, it will recover certain strain. It will go to full. Right? So we assign a recovery ratio M, which is basically, which you can measure actually. You can measure this location and this location. So we call it theta d minus theta h by theta d. That is the measurement of recovery, strain recovery, by virtue of martensitic recovery process. And we conducted certain high temperature XRD experiment to assess the stability of martensite. So this is for the sample which is homogenized at 900 degrees centigrade and quenched to ice drying. We find single phase austenite we obtain only at 200 degrees centigrade, although martensitic start temperature is 63. So even we are concerned, we know the constraint of martensitic transformation by strain or something, we call it stabilization. But here austenite is also constrained. Martensite to austenite transformation is also constrained. So that's how we determine the suitable temperature of aging at austenitic region, and we had to go beyond 300. So this is the room temperature XRD, and here there are a lot of peaks. So we deconvoluted the peak. So this is for homogeneous quench sample. We found significant amount of parent phase, that is between. There is significant amount of parent phase and certain amount of martensitic phase. Now we cold worked, and there we find that we got significant amount of martensite. So amount of martensite is increased by virtue of deformation induced transformation, as we have discussed. The application of strain transforms austenite to martensite. So by deformation, we got higher amount of austenite, and that is true for cryogenic treatment. In our time, we had the habit to move to computer and to shift the screen. So that is driving me, and that is also shape memory. So these are the microstructure. This is a two-phase microstructure. The plates are martensite and the matrix is austenite. This is cold work microstructure where we have very fine precipitates, and this is kind of banded. Actually, during deformation, nucleation and propagation occurs in certain localized manner, where there is strain in the favorable direction of strain. So it is not homogeneous and uniform. So we obtain banded structure. And when we deformed in, and there is no significant difference in size and distribution of martensite. But in case of cryo-rolled sample, we found the bands with very fine martensite and coarser martensite. How easy? And we found there is adiabatic heating. When we were deforming, although we were deforming in cryogenic temperature, by virtue of limitation in conductivity, the material get some region of material in a very localized manner get heated adiabatically, and it has been reported in literature also. In case of copper, it can go as high as 500 degrees centigrade. So this localized heating transforms the martensite to austenite. And during this heating, the strain is relieved, and this austenite, when it attains the room temperature, there is a cooling, and this austenite or B2 phase transforms into martensite, and which are having coarser size because it is unconstrained. There is no strain now. So we have this kind of microstructure. So we found the tensile state. You can see this region, this flat region is basically transformation region. Now we find that in contrast to the earlier tensile curve where I showed a very flat plateau region, here there is a slope. But it is not matching with work hardening slope. Why this slope is that? So this is, as there is heterogeneity in martensite, right? So different martensite takes different stress for recovery. Its stress, different size and shape of martensite, stress takes different level of stress for reorientation, coalescence, like that. This is a region where reorientation and coalitions of martensite occur. So in some of the martensitic region, plastic deformation starts, and this is basically overlapping region of recoverable strain and plastic strain. So by combination of that, it takes a slope. And this is the shape recovery ratio which we have measured as I have shown with the wire, and we can see the cold work sample offers the best shape recovery behavior comparable to cold roll, and this homogeneous coin sample are a bit less. So I will now go a bit fast because many things may not be interesting. We also conducted aging, right? And we observed that at certain temperature, 400 degrees centigrade, and for certain time, we have maximum hardness. So we considered these because our intention was to increase the critical resolve cells. Our intention was to defer the plastic deformation so that we have large region of recoverable strain. So taking that, we conducted the experiments, we found the XRD, and here we found the formation of precipitate phase. So there occurs precipitation, and it is Ti to Ni phase. Now you can imagine what effects can be there. As there is deformation, deformation will cause straining of the matrix, and when there is precipitation, there are three major effects. Number one, as it is titanium rich, so the region around the precipitate will get depleted in titanium, right? And that will change the MS temperature. Second thing, these precipitates will create a coherency stress because it has to make it stabilized within the matrix. So I believe metallurgy students are familiar about coherency strain. So the coherency strain hinders martensitic transformation. But the precipitate provides the surface for nucleation of martensite and helps in martensitic transformation. So role of the precipitate itself is conflicting. So frankly speaking, we were very confused in correlating the structure and property. And we went to the, as I have mentioned in the title, we observed the shape memory behavior of individual martensite plate by nanoindentation. We put it under microscope. And we have taken the indentation on several martensite plates of comparable size. What we find? This is the stress strain behavior. And for nanoindentation experiment, you can measure stress and strain by certain empirical relations proposed by Tabor, right? Where H is the hardness, AC is the contact. It is done by a ball indenter and cyclic loading mode. Someone who is familiar with nanoindentation technique, he can get it. There are two indenters, Barkovich and spherical indenter. We have adopted spherical indenter as recommended for determining stress strain curve. So the AC is contact radius, R is the radius of the indenter, and H is the contact depth. So you can measure H and R physically, and you can determine AC. So that's how we have created the plot. You can see the A sample, which are open circle. See, red one is cold one, black is homogenized and quenched, and green is cryolode. So when you age them, in all the cases, you have seen that there is certain hardening, right? So we have seen the nanoindentation curve for each cycle. This cyclic loading. For each cycle, you can see we need a bit of higher load for initiation of plastic deformation. So there is this exemplifier. This particular diagram exemplifies the hardening mechanism, and moreover, we conducted AFM experiment where we found shrinking effect. In hardness measurement, when there is a shrink in, it infers that it is strain hardening. So strain hardening was confirmed, so we could achieve that much, that we could achieve strain hardening in NITI and expecting the CRSS to increase by that, but we didn't gain anything in terms of shape recovery or strain behavior. Be with me with patience for 1 minute. This is a tensile curve. And from nanoindentation experiment, we determined a parameter which is called recovery index, which is nothing but the area under the loading curve, ratio of area under the loading curve, that is this total area, and area under the unloading curve. This ratio determines the recovery of the sample once you withdraw the indenter, right? And we plotted the variation of recovery index with strain given by tower. We find there is a slope change. And this slope change uniquely coincides the termination of recoverable strain and onset of plasticity in macroscopic tensile experiment. So, the nanoindentation experiment uniquely comply with macroscopic tensile experiment in terms of recovery behavior. So, it seems that, and it is on single martensite plate. So that is how we could correlate this much.
Please conclude within 5 minutes.
Okay, enough for me. As we were confused, the other supervisor of Origi, Professor Shubhabrata Datta, he is expert in soft computing. So he collected the data and tried to correlate the input and output. Input was for deformation amount, deformation temperature, aging time, aging temperature. These were input, and output was hardness, elastic modulus, and shape recovery. So that they correlated, and they developed an ANN model with this input and output, and that model was used in an optimization experiment under genetic algorithm framework using NSGA2 software. to optimize the hardness and shape recovery. And when we find the Pareto font, we find there is a scope of trade-off. I mean, there is change in shape recovery with hardness, right? And each of these points are, this we call optimal solution point. For each point, it is associated with a set of input and output, right? So we increase the solution number in terms of hardness. So this you may consider as a hardness axis. So we found that deformation doesn't contribute much as we analyze the data. Similarly, deformation temperature is below 100 K, is not very effective, which we didn't found when we were conducting experiment. So we created a contour of shape recovery value against amount of deformation and temperature. We found that the maximum recovery value concerns with a deformation temperature of around 100 K and a deformation amount of 0 to 5 K. The whole experiments were almost unjustified, and I was really scared about future of his PhD after conducting so many experiments. We could not conclude anything significant except we could correlate the microscopic and macroscopic behavior. So from that, we thought of doing some experiment at lower temperature. So we homogenized the sample and just quenched it liquid nitrogen without doing it. We conducted cold deformation, we homogenized it, and we quenched in liquid nitrogen. Forget about others. Look at this slide. This is recovery behavior. You can see this particular sample, which is homogenized, quenched, homogenized at 900 degrees centigrade and quenched in liquid nitrogen, offered about 10% of recovery stress, which is highest so far reported in literature. In most of the literature, the recoverable strain is around 7%, 8%. But this particular treatment, which had not been conducted earlier, that offered us a 10% recoverable strain. Right? And we have a very surprising morphology of martensite. Other than in other cases it was coarse, random, but here they are very fine and oriented in one particular direction. That favored the reorientation, coalescence and detuning of martensite, and as a result favored the shape recovery behavior. From nano-indentation experiment we also found significant improvement of shape recovery ratio in comparison to others. That's how I could complete his thesis, and here I complete my presentation. This is actually shape recovery behavior. You can see there is no stress, no strain, no one is pushing, nothing is happening, only there is a heater which is heating and cooling the system, and it is doing this on its own. So I believe if some of my students are there, they understand metals are not only dumb, they are also smart. Thank you.
Audience, if there is any point to be clarified by the speaker.
I mean, students will not ask questions because students doesn't ask questions.
Any student?
You are welcome. You are welcome.
For me?
Okay. So, as you said, it is a phase transformation. So, what kind of phase transformation it is? Is it a first order, second order?
It is first order. Simply first order.
So, you have a huge hysteresis there. Because of that, you are saying it's a first order?
The hysteresis is in terms of strain.
Yeah, when we have strain and temperature hysteresis, as I said. So, and another thing is when we have a lattice invariant strain, let's say in case of ceramic samples or thin clay or single crystals.
Let me tell you, this hysteresis is a characteristic of deformation behavior of
Are
martensite.
you able to hear him?
It is not characteristic of martensite to osmate transformation.
Okay. Another thing, suppose if we have a lattice invariant strain in a system, mostly in case of thin film, if you have a epitaxial film, so this strain usually relaxes and gives a crystal deformation. which may not be may not have the memory effect in case of single crystal mostly. So how in case of said memory alloy this lattice strain driving this kind of phase transition?
When we call it lattice invariant strain, it doesn't change the lattice. That's why we call it lattice invariant. But it is necessary for translating an invariant line strain to invariant plane strain. Under invariant line strain, there is no plane, because for invariant line you need non-parallel set of lines which will be invariant. But any rotation cannot result that. There is no rotation which can result into non-parallel invariant lines, right? So bend distortion model cannot explain martensitic transformation completely. You need an invariant plane, and that you can achieve. There is a plane, there is a shape change. So if you can repair the shape at the boundary and get back the desired shape, the purpose is served. And this influence only the boundary in terms of dislocation and twin. It doesn't change when a slip passes through the crystal, it doesn't change the atomic locations. So atomic arrangement, atomic periodicity remain intact. Only you have certain steps at the boundary. And that's how the interface between austenite and martensite can adjust and remain invariant.
Actually, if we have a purely first order transition, hysteresis is the most prominent signature of that, and it gives you his memory effect in first order transition.
It may be that is magnetic memory.
In case of normal, suppose if you heat up a water, it will become gas. If you cool down, it will be back to liquid state.
It can be there. It can be there. It happens in magnetic memory effect. But in case of mechanical memory effect, it concerns only the mechanical behavior of martensite. Right? It doesn't. This hysteresis is not involved in transforming martensite to austenite, and it doesn't bring in any discontinuity in specific heat or other second derivative parameter of free energy.
Audience, is there anyone? Any clarification further?
Thank you. Jeans hoga? This is for jeans. This question is for jeans.
No, sir.
Bolo.
Sir, it was nickel and titanium. So if we are adding a 0.85% of vanadium to increase the ductility or some fraction of molybdenum, so we will get more elongation
It is not elongation. Elongation means there are two elongations here. One is recoverable and other is permanent.
Yes.
You can increase permanent elongation, right? Shape memory alloy, NITI alloy is also used for structural purpose, say for biological implants, right? Where they need to optimize the strain and elastic modulus. So that's why they go for alloying, because it has to match. For nickel titanium, the modulus is higher than the bone. So they need to match the modulus of nickel titanium alloy with that of bone, right? So that's why they do alloy. But here, yes, you can do alloy, as we have done the cold deformation and aging treatment. You can also do it, but you have to make sure the recoverable strength. In our case, for cold deformation and aging, we obtain a recoverable strength to the level of 5-6%, which is lower than that reported in literature. So our work could not have any value until and unless we could have this enhancement. So yes, that can be tracked. I am not familiar with, and more importantly, if you add something, you may not get the line compound in it. It is a line compound. You have seen the composition is 50-50.
Yes.
And it varies within a very close range.
Yes.
So if that stoichiometry is disturbed, you need to consider thermodynamics.
So that is why I said 0.85, which
Whatever
is
it
not.
is. It can be even 2. I don't mind. There are ternary intermediate compounds. That is not forbidden. You can do that. But you need to consider the thermodynamics first. What happens to the enthalpy value of NITL?
Thank you. Due
Thank
to
you, sir.
time constant, let us invite another speaker. And please everyone who is interested he or she. Thank you, Professor Chattopadhyay.
It's my pleasure, sir.